Assalamualaikum and hi everyone. So today you are going to learn a new chapter which is pressure. First subtopic is 2.1 pressure in liquids. So this is just an activity, a very simple activity that you can do at home. So this activity is used to investigate the relationship between depths of water and pressure of water. So if you do this activity, you will find out that as pressure increases with depth of water. So the lowest, okay, so if you can see, this is water and we make some holes on the bottle and we can see that water will spurt out from the holes. So from your observation, you can see that the lowest hole of the bottle will exert the furthest water. The spurt is the furthest, which means that the pressure below is the greatest. Compared to the pressure at the top, it is the lowest. This is because the greater the height from the surface of the water, the greater the pressure. So for the second activity, you are required to poke holes at the same level. So when you make holes, you will see that the water spurt out at the same distance with each other. This is because the level of holes are the same. So the pressure is the same. Okay, so what is liquid pressure? So pressure at the base of liquid column is caused by the weight of the liquid column. So let's say we have a column of water. So the pressure at the bottom, if there is an object at the bottom of the column, it will experience pressure that is caused by the weight of the water above it. Okay, liquid pressure can be calculated by using the formula pressure equals to H times rho times gravitational acceleration, where H is the depth of liquid, rho is the density of the liquid, g is the gravitational acceleration, which is a constant value. SI unit for pressure is similar to the pressure that you have learned in lower form. So in lower form, you have learned that formula for pressure exerted by a solid object is force per area and the unit is Pascal. So similar to that, liquid pressure has the same unit, which is Pascal. In example 1, so here the figure shows a submarine traveling from the surface of the sea to a depth of 6,000 meter. If the density of the water is 1025 kg per meter cube, calculate the pressure exerted by the seawater on the submarine at that depth. So we are going to do this example. So the formula for liquid pressure is pressure equals to height times gravitational accelerations times rho. Rho is the density of the liquid acting on the object. So height is 6,000 meter. Make sure the unit is in SI unit. Gravitational acceleration 9.81 and density of the liquid is 1025 kilogram per meter cube. So you will get 60331,500 Pascal. So this is not a very nice form. You have to convert it to a standard form, which is 6.03 times 10 to the power of 7 Pascal. Okay, so here from the answer, we know that as the depth increase, the depth from the surface of the water increase, the pressure will increase. So let's say the submarine rises to a height of maybe 100 meter. So let's say you are required to find the pressure acting on the submarine when it is 100 meter below the surface of water. So use the same formula. So now height is 100 meter times gravitational acceleration 9.81 times the density 1025, and you will get 1005.525 Pascal, or if you read it in a standard form, it is approximately 1 times 10 to the power of 6 Pascal. Okay, so this is a lower pressure compared to when the submarine is at 6,000 meter height. 6,000 meter depth. Okay, let's take a look at example number 2. So in this diagram, a farmer is trying to draw water from a pond at a nearby hill by using a metal pipe. So you can see that water rushing out of the holes at the lower end of the pipe irrigates his plants. So the farmer is trying to water his plants using the water from the pond. Calculate the pressure of water rushing out of the holes. Okay, so the pressure of water rushing out of the holes can be calculated using formula P equals to rho GH. So rho is the density of water, which is 1000 given from the formula, times gravitational acceleration 9.81 times height. So height here is height from the surface of the pond, which is 16 meter, and you will get 156.960 Pascal, or in standard form 1.57 times 10 to the power of 5 Pascal. Okay. Okay. So next, so in laboratory, we have one apparatus that can measure pressure, liquid pressure, which is called U-tube manometer. So the shape is in U. So here we can see that if we pour a liquid, for example in this diagram, we pour liquid X into the U-tube manometer, and the level of the liquid left and right will be the same. So here I have, on the left side, I have A, and I will label A, the pressure at A is pressure A, and at B, the pressure is PB. So here you can see that the level of A and B is the same. So when the level is the same, then the pressure at that point must be the same. So pressure at A is actually equals to pressure at B. Okay. So what happens if we have two different liquid with two different density? So similar to the above diagram, even though the height is not the same, but if we take 2 points of the same level, so in this diagram here, 2 points of the same label is A and B. So let us make a dotted line there. Okay, so at A and B, since the level is the same, then the pressure should be the same as well. So PA is equals to PB, even though the density is not the same. So at point B, it feels the pressure exerted by liquid Y. So you have to calculate using density of liquid Y. Whereas for A, it experiences pressure exerted by liquid X. So you have to use density of liquid X. Okay, so here we have pressure A equals to pressure B, and let us break it down. So you already learned that P is rho GH. So you have to break it down one by one. So pressure of A is rho A times gravitational acceleration times height of A equals to rho B times gravitational acceleration times height of B. Okay, so let's do a simple exercise. Figure below shows a U-tube filled with water and olive oil. The density of water is 1000 kg per meter cube. Calculate the density of olive oil. So first, you have to take 2 points of the same level, which I'm going to label with dotted line here. Okay, so I'm going to label here as A and I'm going to label here as B. So pressure at A is equals to pressure at B. So, okay, let's do it down here. So pressure at A equals to pressure at B. So break it down into its own component. P at A times gravitational height times height at A equals to rho. I'm sorry, it's not P, it's rho. Rho B times G times height at B. Okay, so density of A, since A experience pressure exerted by water above it, so you have to use density of water. So density of water is 1000 kilogram meter cube times gravitational acceleration. Okay, so here, before you proceed, you can see that on the left side we have gravitational acceleration. So similarly, on the right side we also have gravitational acceleration. So we can cancel this out. Okay, so that leaves you with density and height on the both sides. Okay. So 1000 times height of A. Height of A is 15 centimeter, but don't forget you have to convert to meter. So it is 0.15. Density of olive oil is unknown times height of olive oil exerting on point B, which is 16.5 centimeter. So let's convert it to 0.165. So density of olive oil is actually 90.9 kilogram per meter cubic. Okay, so I think that's all for this video. Thank you.